Hello everyone, and welcome back to another video. Today in this week's video we're going to be talking about logarithms, which are a function that some of you may have some experience with already, but we're gonna dive into them today. They're a little bit complicated, so be sure to pay attention, but they're definitely pretty useful and definitely an interesting part of mathematics. So what is a logarithm? Well, let's first start off with the inverse of a logarithm. So the inverse we know of a function is basically the opposite. So for subtraction, the inverse is plus, because to undo it, which is like what we would call an inverse in math, when you undo addition, you're subtracting. So if you add 2, if you want to undo what you just did, you do the inverse of addition. You subtract 2. So the opposite of a logarithm is what we call an exponent or an exponential function. So for instance, you might have 2 to the third power. That's an exponential function. That equals 2 times 2 times 2. So what is a logarithm then? So if that's our function, an exponential function, and we want the opposite of that, we want the inverse, well, what is that? So that equals 8. Well, a logarithm says you write it as log. Down in the corner, right below the log, what we call a subscript, is what you call the base of a logarithm. And then in the stomach of the logarithm, we have some number, and it equals something. Just like we have like 2 to the 3 equals what? Well, we solved it for equals to 8. So the inverse of that in this case would be the base, what goes in that bottom, is what is in the bottom of our exponent, 2. So our exponent has a base of 2. So our log is going to have a base of 2. So we write log 2. But what goes in the stomach here? Well, because it's the opposite of an exponent, it's what we call the inverse. It's not 3, it's actually 8. So that would mean that it equals 3 because we just switched the 8 and the 3. So now it's like log base 2, we say, because 2 is in the bottom, of 8 equals 3. Well, if we write it in exponential, we say this number in the bottom to that power must equal what's in the stomach. So if we have log, and this is generic, a general formula, if we have log base A of B, and it equals C, well, we write A to the power C must equal what's in the stomach, what's inside our log, B capital. So you can see how they're related. They're inverses of each other. So let's quickly do another example of a log. So let's say that we have log base 10. So here in this case, in math, we assume that if you don't have a base written, so some of you who might have seen logs may have just seen like log 100. And you're like, well, where's that number in the bottom that we call the base? Well, when we don't see one in the bottom, in math, we just assume that it's 10. So in this case, log 100 is really the same as saying log base 10 of 100. So how do we solve that? Well, that's like saying 10 to what power, because we like turning it into exponents because we're more comfortable with that. We have more experience with powers. So 10 to what, we can call it A, equals 100. Well, at first glance, we think, well, 10 to the power 1 is 10, 10 squared, well, that's 100. So a equals 2. So then from that, we can solve our log. So log 100, or log base 10 of 100, equals 2. So that's another example of a log and how we solve them. So just, it's very important to remember that if you don't see that number in the bottom right here, we assume that it's 10. Otherwise, if there is a number, let's say it's log base 4 of 64, well, that's 4 to what power equals 64? Well, 4 squared is 16, so it's not 2. 4 cubed, though, is, that's 64. So a equals 3. So log base 4 of 64 equals 3. So that's how we solve logs. So now we're going to talk about some very special properties of logarithms. So let's start with when we have two logs added together. So let's say that we have log of 5 plus log of 2. Well, what does that equal? Because when we first look at that, we're like, well, we know that we can write these as log base 10 of 5 plus log base 10 of 2, because if there's nothing written in the base, in the bottom right there, we just assume that it's 10. That's just a general rule in math. But when we look at that, we don't exactly see an answer right away, because 10 to what power is 5? Well, that's a little weird. And 10 to what power is 2? Well, that's also weird. So we're thinking, well, how do we solve this? Well, there's a very special formula or property of logarithms. When you have two logarithms added and they have the same base, so see how we have 10 here and we have 10 there. We can write it as one logarithm with the same base, and inside we multiply the bases of each respective log. So in this case, 5 times 2, which equals log base 10 of 10, which is, 10 to what power is 10? 1, so we solved it. So let's go over that one more time, because it might be a little confusing. And then we'll show why that works, because it might seem like, why does that work? That doesn't really make much sense. Well, let's just do one more quick example. So that's like saying if you have log, let's say base 3 to the, and then inside of that, let's say that you have, let's say you have 3 plus log base 3, and let's say you have 27. So obviously we could solve each log individually, meaning what is log base 3 of 3? Well, that's 1, because 3 to the power 1 equals 3, so that answer is 1. And this is 3 to what power is 27? Well, x in this case is 3, right? It's 3 cubed is 27. So the answer to this log is x, which is 3. So that means the answer is 1 plus 3, which is 4. But let's just make sure that our property, what we just showed, our little formula thing, works. So first we have to make sure they have the same base. They do, both 3, so we rewrite it. Then we multiply the inside. So 3 is in the inside of the first one, 27 is in the side of the stomach of the second one. 3 times 27 equals 81, right? So it's 381. Well, that equals what? Well, 3 to what power is 81? Well, it's 3 to the 4th. So our answer is 4. just like we solved when we solved for the logs individually and then added. We got 1 plus 3, which is 4. And when we multiplied the insides and used our addition trick for logarithms, we also got 4. So that just shows that it works. Well, let's see why it works. For what reason is this property successful? Why is it a thing that we can use in math? Because it seems a little bit arbitrary, a little bit random, that although it works, we're kind of like, well, why? So let's try and prove it. So to prove it, let's look at one more property of a logarithm. So that property is, and this is pretty simple, if you have log, and let's say that the base you're using is just a, some number, and inside your log, you have a to the power x. Well, what is the answer to that? A to what power is a to the x? Just x, right? So when we have a to the power x and our log is base a, it's just this number up here. So that just equals x. So now let's look at this proof. So let's say that we have log, and let's say it's base b, and inside we have m times n. Well, we're going to show later, we'll eventually prove it, that equals log base b of m plus log base b of n. We're going to prove that. So let's start with this side of the equality, though. Well, we just showed that we can actually rewrite this as log base b of b to the x times b to the y. Some of you might understand that, but it's a little bit confusing. Why can we say that that is true? Well, the answer is because we can say that log b of m is going to equal x by definition of a log. It's going to equal some number, and log base b of n is going to equal y. So by substitution, we can just plug that x in and that y in. Because remember this formula right here, or this property. So let's just rerun through that a little bit more concisely so that it makes more sense. So basically what we did is we said, by definition, log base b of m is going to equal some number x. We know that that's just how it works. We don't know what x is, but it's going to equal some number. And log base b of capital N is going to equal y. By some number, we know that that is true. Well, why can we just plug in b to the x for m and b to the y for n? Well, remember what the definition is of a log. It says that b to the x equals m, and b to the y equals n, because we say b to what power equals m? Well, x. We don't know what x is, but we do know that b to the x equals m. And the same thing is true for n. So we can just plug in where we had m and n up here, we just plugged in b to the x and b to the y. So now we can use a property of exponents. So some of you might know this property, but basically if you have a to the power z times a to the power y, it equals a to the power z plus y. So we'll maybe prove that in another video, but that's a property of exponents. When you have the same base of the exponent and you're multiplying, you can add the powers. So we added z plus y. So here, inside of our stomach of our logarithm, we have b to the power x plus y. We just used the same thing we proved down here. So let's continue. Well, based on our formula from our property from up here, that x plus y is the solution to our log. Because remember, x, what was in the power when we had the same base, remember we had a and a, here we have b and b, so it's just what's ever in the power is the answer. So that just simplifies to x plus y. Well, x plus y equal log base b of m plus log base b of n. So we proved it. We said log b of m times n equals log b of m plus log b of n, just like we said at the very top. So that's our proof for that. And now let's look at one more property. And this property, we're going to have to use actually what I just erased, where we have log base b of b to some power, let's say x, equals x. So we're going to use that to prove this cool property. So this property is if you have log base b of m to the p. So that right here is actually a special case. That's where b equals m. So here, it's actually, we can prove that it equals p times log base b of m. So what happened? Well, this p that was in the exponent of the stomach of our log just came into the front. So let's prove why that works. Well, first, we're going to use, again, the basic definition of a log. So log of b of m is going to equal some number x, meaning b to the x equals m. That's just our definition of a log. That is always true. Log b of m is going to equal some number. We don't know what it is. Let's just say that it's x. So therefore, b to the power x equals m. So we can plug in where we have m. So we have log base b of b to the x to the p, because we plugged in for m. Well, another exponent rule, we can multiply x and p, because when you have b to the x to the p, that's really the same as just b to the x times p. We can bring down that p kind of one level. So it's really just b to the x times p. So let's write that again. We have log base b of b to the x times p. So now what can we do? Well, now we can use that property that's pretty simple up here. It's just when you have b as the base and b as the base of the exponent inside of the log, like here, it just equals the power of b inside of the stomach. So in that case, it's xp. So this just equals x times p. But what does x equal? Remember this. So we can rewrite that as p times x, which equals p times log base b of m, just like we set up here. So that proves that property of logarithms, which is super helpful. So one last rule or property of a logarithm that we're going to mention in this video is the quotient rule. Or really, it's the opposite of that product rule that we said earlier, or we proved it earlier, was log of b of m times n equals log base b of 2m plus log base b of n. So the addition of two separate logs. Well, this is the opposite. This is just log base b of m divided by n equals log base b of m. And some of you can guess, the opposite of multiplication is division. So the opposite of addition, subtraction. So we're actually not going to prove that one because it's basically the exact same steps we used to prove the first property. But so that one also is kind of intuitive because you use subtraction instead of addition for this division rule when we had multiplication. They're kind of inverses of each other. So that rule we can prove in the exact same manner, but we're not going to. But it's definitely important that you know that property. So actually, one last formula or rule of logs that we're going to prove is a little bit more complicated, but it's super important and super useful. It's the change of base. So it basically says log base b of a equals log of a divided by log of b. So that would be base 10 for each, since we didn't prove it. I mean, not that we didn't prove it, that we didn't write it. Remember that if we don't write the base, so that number right here in the bottom, just going to draw it as like a little circle, we never wrote that, which means we just assume that it's 10. But actually, it could be any number. So it could be log base 3000 of a, but it has to be the same on the bottom and the top. So it'd be log base b of a equals log base 3000 of a divided by log base 3000 of b. But obviously, when are we going to use 3000? So we're just going to leave it as base 10, and that's what the common formula is. So it's really just written as log base b of a equals log a divided by log b. That's the most common, and you'll only see that one. And it's called the change of base. So let's quickly just show why that works. So let's say that we have log b of a, and let's say that equals some number y. We don't know what y is, but again, we'll just say y. For simplicity, we can just say it's some number. So then by definition of log, b to that power y equals a. So that's the definition of logs. It's super important to know that. And then from there, what we're actually going to do is a little bit complicated. We're going to take the log of both sides. So just like when you're solving algebra problems and let's say you have x minus 3 equals 7, it equals 10, right? But really what you do is you add 3 to both sides, and you get that x equals 10 because these 3's cancel. The key is you did the same thing to both sides. Well, here, we're going to do the same thing to both sides. We're going to take the log of both sides. And here's why, like I said, it could be 3000, and that base could be anything as long as it's the same. It's because right here, when we take the log of both sides, we can take it the log base anything we want. 3,002,400, anything you want. We're just going to take it log base 10 for simplicity. So we write log. We're not going to write base 10 because remember, we don't have to in math. We just assume. So log base b of y equals log base 10 of b to the power y equals log base 10 of a. We took the log of both sides because we can do the same thing to both sides when we have an equation. And that equation then is still equal. So now we're going to simplify this. We just looked at a property where we can bring that y to the front. We just proved that. So this equals y times log base b, which equals log of a. We're going to divide by log of b, both sides. So we get y, y equals log of a divided by log of b. Well, what does y equal? It equals what we started with originally. So it equals log base b of a, and that equals log a divided by log b, just as we proved. Just as we said we would prove at the beginning. So that's the proof of the change of base formula. So we've gone through a few properties. We've gone through This one up here, the addition of two logs, we've gone through this property down here where we brought that y in front. So that's one property. And then the special case of that, sort of in a way, is we said log base b of y. Well, we can bring that y in front. So it's really just log base b of b. But that equals 1. So it's really just left with y times 1, which is why that equals y. Sorry for the double y, but that is a special case, and we looked at that. We looked at the division rule later, up here, which is, or that's actually the fourth one now, which is sort of just the opposite of that first rule, the multiplication and addition. Now it's just division and subtraction. And then fifth, but probably one of the more important ones, is the change of base. So log base b of a equals log base 10 of a divided by log base 10 of b. And remember, 10 we just chose because we like to use base 10, but it could be base anything. It could be 3,000. It just has to be the same on the top and on the bottom. And just quickly, I just mentioned something. We like to use base 10, and I'm just going to explain why really quick. So base 10, I'm just going to write down here, is what all of our numbers are in. So 384, that's in base 10. The reason is because we can write it as the sum of powers of 10. We can write it as 3 times 10 squared plus 8 times 10 to the 1 plus 4 times 10 to the 0, because that's really 3 times 100, which is 300, plus 8 times 10, which is 80, plus 4 times 1, so it's 384. So that's just why we always use base 10, because when we use expanded notation, you can see all of these terms are base 10, all these powers. So that's just why we use base 10. And it's why we sort of just assume if you have log of capital A, that really just equals log base 10 of capital A. So I hope you enjoyed the video. It was definitely a brand new concept, so it might be super confusing to some of you, but as you do problems, and if you watch this video maybe once or twice, you will begin to understand it. But of course, if you have any questions, anything at all, feel free to email us, and we will get back to you about that question. And it doesn't have to be just about the video. It could be about any math or any question you have about what time our lessons are, a question in the problem set, anything at all. Just email us. So yeah, I hope you enjoyed the video, and good luck in the problem set, and hopefully we see you at our Zoom meeting later in the week. Thank you.